Welcome to the Deep Dive. We take your source material, strip away the noise, and really get to the core of what's happening.
That's the plan.
Today, we're diving into a really fascinating space, I think, where cutting-edge tech meets, well, ancient structures.
Yeah, it's a cool intersection.
We're talking about using 3D printing, but not just for, making nice replicas. This is about actually repairing and restoring historical architecture.
And crucially, we're looking at how that printed stuff performs structurally. Can it actually hold up? We've been digging into a research paper that did some real hands-on testing.
Exactly. Testing components made from a material that maybe you wouldn't first expect for this kind of job.
It's an interesting choice, for sure.
So our mission today is to really understand the potential here. Can we use 3D printed elements, especially from sustainable materials, to restore old buildings? Based on the actual experiments in this paper by Tomei, Grande, and Mbimbo.
Yeah, moving beyond just aesthetics, we're asking, can these parts bear load? Can they be structurally integrated?
Forget just printing statues, right? This is different.
Totally. And the study, well, it has some genuinely interesting findings,
About the material, yeah.
but also about designing these printed parts efficiently.
Okay, let's unpack it. Maybe start with the basics. Just how complex is architectural restoration? What are the main headaches?
Oh, it's incredibly complex. You're dealing with unique buildings, often centuries old,
Right.
sometimes intricate designs, bits missing. You need custom parts, obviously, that match the look and the form.
Uh-huh.
But, and this is key, conservation principles say you've got to minimize intervention. Preserve as much of the original as possible.
And I guess traditional ways of making replacements, like carving stone or casting, that takes ages, right?
Yeah.
And specific skills.
Exactly. Slow, needs specialists, often produces a lot of waste material too.
Okay.
And that's where 3D printing kind of steps in with some potential real advantages.
Right. So 3D printing, additive manufacturing. The paper talks about fused filament fabrication. FFF, that's the more common type, like desktop printers.
Yeah, that's the one. Building things layer by layer, extruding heated plastic is fantastic for complex shapes, stuff that's super hard or expensive to carve or mold traditionally.
And the whole process fits restoration well, doesn't it? You can 3D scan the building or even just a broken piece.
Precisely. Use scanning or photogrammetry to get this incredibly precise digital model of what's missing or damaged.
Okay.
Then you take that digital file, feed it to the printer, and boom, you get a replacement part with high accuracy.
Much faster for tutorial designs, I bet. Less waste, too, compared to carving from a block.
Definitely less waste. The paper actually mentions some examples where this is already happening.
Oh, yeah.
Like reproducing detailed Roman cornices, museum bits, fixing ancient statues, making ornaments, using cement-based 3D printing in some cases.
Interesting.
But this study, it takes a bit of a different path, looking at polymers, not cement.
Which brings us to the material they used. PLA, polylactic acid. Now, like I said, PLA makes me think of, I don't know, disposable cups. Or maybe hobbyist prints. Why PLA for architectural restoration?
That's a really good question. And the authors tie it straight back to core conservation ideas, like the ones from ICOMOS. First off, recognizability.
Recognizability.
Yeah, PLA is plastic. If you use it to patch up some old stone or brickwork, it looks different. You can easily tell what's original masonry and what's the modern repair. That's important for the building's historical honesty.
Okay. So you're not faking it. It's clear it's a repair.
Exactly. Second point,
Right.
reversibility. PLA is biodegradable. Now, it usually needs specific industrial composting. It won't just melt in the rain.
Right.
But the fact it can break down eventually aligns with that principle of minimal intervention. The repair isn't necessarily permanent like some modern epoxies might be. You could, potentially, remove or replace it later.
Okay. So it respects the original structure long term.
Yeah.
Makes sense.
Precisely. Third, sustainability. PLA comes from renewable stuff like cornstarch, is bio-based, generally seen as greener to produce than, say, petroleum plastics like ABS. And fourth, affordability. PLA filament is pretty cheap. That makes it viable maybe even for temporary fixes or just trying things out on a large scale.
So recognizability, reversibility, sustainability, affordability sounds good, but
But can it do the job?
yeah. That's the big question, right? Beyond looking okay and ticking those conservation boxes, can PLA parts actually perform? Especially if they have to carry some weight.
Absolutely critical point. If an element needs to integrate structurally, even something mostly decorative, like a heavy cornice or part of a parapet looking right, isn't enough.
Needs the muscle, too.
It needs adequate mechanical properties. Strength, so it doesn't break. and stiffness, so it doesn't bend or sag too much under load.
And this is where 3D printing gets complicated, because the final strength isn't just about the plastic itself, is it? It really depends on how you print it.
Hugely.
Mm.
Layer orientation, nozzle temperature, print speed, how solid the inside is, all of that drastically affects the final strength and stiffness.
And the paper highlights this gap, right? Lots of work on printing pretty replicas, lots on basic PLA properties, but not much looking specifically at the structural behavior of actual components made from PLA for this purpose.
Exactly. Most studies use simple shapes, or didn't really push the structural limits. This research wanted to test components designed with architectural reality in mind.
So how'd they set it up? What did they actually print and test?
They tested two main kinds of samples. First, standard shapes called dog bone samples, the ones narrow in the middle.
Yeah, I've seen those.
They're designed specifically to test the basic material properties.
Mm-hmm.
How strong and stiff is this specific PLA, printed with these specific settings?
Okay, getting the baseline for their material and process.
Got it. And second, they tested truss-based beam samples. These were designed to mimic a lightweight structural panel, something you might actually use. They wanted to see how more complex, realistic shape holds up.
And all printed using that FFF method.
Yes. Specific machine, controlled settings. The paper lists all the details, but the key things are standard PLA filament, layer thickness, 0.25 millimeters, and importantly, the outer walls were printed with 100% infill. So those edges were solid plastic.
Those settings matter a lot, I guess.
Oh, completely. Change the settings, you change the results.
Okay, so they print the samples. How did they test the dog bones?
For the dog bones, standard tensile tests. Basically, grab each end and pull until it breaks.
Okay.
That tells you the material stiffness, its Young's modulus, and its ultimate tensile strength, the maximum pulling force it can handle.
And the truss beams, what was that truss design about, and how'd they test those?
The beam design was smart, continuous outer edges like a frame, but the inside, not solid. It had this internal structure of triangles, a truss, lightweight but strong.
Ah, saving weight, saving material.
Exactly. They actually tested two versions with different internal triangle angles, 60 and 72 degrees, just to see if that made a difference.
And the test.
Two types for these beams. Tensile tests, again, pulling the ends, and also three-point bending tests.
Bending, like pushing down in the middle.
Yep. Supported at the ends, pushed down in the center. That simulates loads on, say, a horizontal panel or maybe a cornice element, more relevant for many architectural uses.
Right. Okay, so pulling and bending, what did they find? What were the results? Let's start with the basic dog bone tests.
Okay. From pulling those dog bones, they got the core numbers for their printed PLA. Average stiffness, the Young's modulus, was about 1,270 MPa. Average tensile strength, 44 MPa.
What do those numbers mean practically? Is 44 MPa good?
Well, MPa is megapascals, a measure of pressure or stress force per area. 44 MPa tensile strength is actually quite respectable for standard 3D printed PLA. It's not steel, obviously, but it's strong for a common plastic.
And the 1270 MPa stiffness?
That tells you it's reasonably rigid. It won't stretch like rubber. It holds its shape pretty well under load. And importantly, these results were very consistent. Low variation between samples.
Which is good if you want reliability.
Absolutely vital if you're thinking structurally. Now, for the truss beams under tension, the pulling tests, they saw what's called elastic brittle behavior. Meaning they stretched predictably under load, that's the elastic part, but then failed suddenly once they hit their limit, the brittle part. No slow yielding or stretching before breaking.
Did that internal triangle angle matter in these tests?
Interestingly, not really for the tension tests. Both the 60 and 72 degree designs behave very similarly. Stiffness was around 2.54 kilonewtons per millimeter.
So it took about 2.5 kilonewton of force to stretch it 1 millimeter. How much force is a kilonewton, roughly?
Think of it like the weight of about 100 kilograms, or 220 pounds. So 2.5 kilometer stiffness is pretty decent, and their strength was about 6.4 kilonewtons.
So they could handle pulling force equivalent to maybe 640 kilos over 1,400 pounds before snapping?
Roughly, yes.
Yeah.
And again, very consistent results. Failure usually happened near the grips, which is expected.
Okay. And the bending tests on those beams, similar behavior.
Also, brittle failure. They bent a little bit, then snapped quite suddenly. The peak load they could handle in bending was around 5 kilorem.
So about 500 kilos, 1,100 pounds, pushing down in the middle.
Yeah, around that mark. And they only bent maybe 3 or 4 millimeters downwards before they failed. Again, high reproducibility, especially for the samples that had a little groove to hold the loading cylinder properly.
Yeah.
Failures usually happen right under that load point.
Okay, so we have the material properties from the dog bones and the performance of the beams. How do they link up? Did the beams fail when the stress hit that 44 MPa number from the dog bones?
Ah, that's the crucial connection they made. They took the forces measured in the beam tests and calculated the force per area happening inside the beam material at the point of failure.
Right.
Then they compared that calculated stress to the 44 MPa strength they got from the simple dog bone tests.
And what did they find? Did it match?
For the beams pulled in tension, yes, excellent agreement. The calculated stress at failure in those beams was right around, you guessed it, 44 MPa.
Wow, okay.
Which is great. It confirms the material properties measured in the simple test hold up in a more complex component. Consistency across different tests, even different labs were involved.
That's really reassuring. What about the beams tested in bending? Did they also fail when the calculated stress hit 44 MPa?
This is where it gets interesting. No. The calculated maximum bending stress when they failed was actually higher, around 51 MPa.
Huh. Why would it seem stronger in bending than just being pulled apart? That seems weird.
It does seem weird at first, but there's a good reason, and the paper explains it. It's all about how the stress is distributed across the beam's cross-section.
Okay.
In the pure tension test, that pulling force is spread pretty evenly across the entire cross-section. Every bit of plastic is feeling roughly the same stress.
Right. Uniform pull.
But in bending, it's different. Imagine the beam bending downwards. The top surface gets squashed, compressed. The bottom surface gets stretched, tension. And the stress is zero right in the middle, and it increases as you move toward the top or bottom edge. The maximum tension only happens right at the very bottom fibers.
Ah. So, unlike the tension test, not the whole cross-section is experiencing that peak stress.
Exactly. Pure tension is tougher on the material overall because the whole area is stressed to the max. In bending, only those outer edges hit the peak stress. So even though the calculated peak bending stress reached 51 MPa, it doesn't mean the material magically got stronger.
Okay.
It's more an effect of how bending stress is calculated and how localized that maximum stress is. It's a known phenomenon in material science.
That makes sense. It's about where the stress is concentrated. Okay, so the really cool part, how did that truss design, the hollow inside, make the beams more efficient than just a solid block?
This is a key takeaway for actual restoration work. The researchers did a calculation. They looked at a specific bending force, say 3 kilonewtons,
Okay.
and figured out the stress in the outer edges, the flanges, of their lightweight truss beam. It was about 34 MPa. Then they estimated what the stress would have been if, instead, they'd printed a solid panel with the same outer dimensions.
And the difference.
Huge. The estimated stress in that hypothetical solid panel under the same 3 kilowan load, a massive 176 MPa.
Whoa! That's like 5 times higher.
Exactly. It's a dramatic demonstration. Using that internal truss structure, even though it's mostly empty space, makes the component way more efficient at handling bending loads compared to just a solid piece of the same rough size.
Because the material is put where it counts most for bending.
Precisely. Placed strategically to resist those bending forces.
That's really powerful. It shows how smart design really leverages the material in 3D printing. So, wrapping this up a bit, what are the big practical implications from all this testing?
Well, the results strongly suggest that 3D printed PLA, if designed cleverly, like with these internal trusses and printed carefully with controlled settings,
Yeah.
can achieve mechanical properties good enough to be seriously considered for structural or at least lightweight elements in architectural restoration.
So, where might you actually use this?
Think about replacing missing bits of decoration on walls, battlements, parapets, maybe complex facade ornaments.
Okay.
Instead of carving a heavy stone block or using dense mortar, you could print a custom-fit, lightweight PLA part with an internal structure giving it the stiffness and strength it needs, but without dumping a lot of extra weight onto potentially fragile old masonry.
And it still meets those conservation goals. It looks different. It's PLA, so it's notionally reversible long term.
Exactly. You get the custom shape, less load on the old structure, and you're following those conservation ethics.
Now, every study has limitations. What did the authors point out here?
Sure. They note it was exploratory, relatively few samples, 22 in total. Good reproducibility, but ideally you'd want more for full statistical confidence.
Right.
And the results are very specific to the PLA they used in the exact print settings. Change those, and the properties would likely change too.
And they only tested immediate strength, right? What about years down the line?
That's the big unknown, and a key area for future work. This was short-term static load. We need to understand long-term stuff like creep deformation under constant load over time, and how environmental factors, moisture, sunlight, temperature changes might affect PLA's properties over decades, especially given it is biodegradable eventually.
So a crucial first step gives us data for computer models, but the full picture needs more research.
You got it. The data they generated is super valuable for building and checking computer simulations. That lets you predict how bigger, more complex PLA parts might behave without printing and breaking hundreds of them. Speeds up design massively.
So where does this point? What's the exciting next step?
Well, it really opens the door to designing and testing larger panels, maybe modular systems. The aim is to move towards pilot projects, actually trying this out on real restoration sites.
Okay, so summing up this deep dive. 3D printed PLA, when you design it smartly with internal structures like trusses and print it carefully, it shows real mechanical promise, enough to be a serious option for structural or lightweight parts in restoration.
Definitely. It offers that unique mix. Custom shapes, respecting reversibility, and being much lighter than traditional options or just solid printed parts.
It's fascinating, really, seeing material science and clever design opening up new ways to preserve our history.
It really is.
So here's a thought to leave you with. Given this potential PLA is shown, especially with smart internal designs, what happens next? If we start exploring different internal shapes, maybe tweaking print settings even more, or perhaps even blending PLA with other materials, could we unlock even wider uses for preserving buildings, maybe even in really tough climates or environments? Something to think about as this tech develops.